Okay. I originally told my don't lose your head joke right before class, but everybody heard that, apparently. I said that I do have more jokes, enough to fill 3 reservoirs. I love my job. I'm such a dork. Okay. In the interest of moving along with the class, let me mention a couple things real quick. So my apologies. I said I would get the exam graded by Wednesday. Take your hand. So take my hand and smack like that. Yeah. You're right. You're right. I deserve that. My goal is to get it graded by Friday. But speaking of, I do want to talk about Friday. So the president of the ASCE student chapter has arranged a tour of Steel of West Virginia. This is a steel design class. So I feel like it might be relevant. That was a joke. Not a very funny one. Of course it's relevant. What's that? Well, here's the deal. Okay, so first off, I'm going to pass this around, but I want to talk a little bit about the logistics. The tour doesn't start at 11. It starts at 10. Okay, so it starts before class. And I know that there's some of you, at least I know there's some people in this class that work that actually couldn't make it. Okay, but I am interested to see who can make it. At a minimum, what I'm going to do is excuse any absence for anybody that's interested in going. If you are interested in going, just make sure that you bring closed-toed shoes and make sure that you're wearing pants, no shorts. I mean, it's a steel production facility, so there might be sparks and all that jazz. First off, I'm going to pass this sign-in sheet around. If you are interested in going, put your name and email address on there. Friday, we were going to talk about slip-critical connections, but slip-critical connections is actually a pretty easy topic to understand and a pretty easy topic to employ. So I kind of want to hit the ground running in class today, and then we'll discuss here at the end, let's see where we get as to what we do with class on Friday, because I may continue to have class, I may cancel class, I don't know. I want to see where we get.
How long does it last?
The tour is supposed to start at 10. They have it blocked off from 10 to 12. They said it might not go that long, so they said they'll have the tour at 10 with time for questions. They said we should be out by noon. They'll provide all the personal protective equipment, just make sure that you don't wear sandals or anything, you know.
I got an exam at 1.
You'll be back by then. So. Yes, it's this place back here. You're going to meet in the pavilion between the 2 engineering buildings, that awning, at like 9:45, if you're interested in going.
Are you going to go?
It depends on how far we get. So that's why I kind of want to jump right into class. So, because I might go ahead and talk a little bit about slip critical connections. So, and maybe try and do it all at once. Everybody good? All right. I want everybody to sort of pay attention because we got to rock and roll on this. Let's talk about bolted connections. So we have bolt shear and bolt bearing capacity. Is everybody okay with that analysis? I know we've had some challenging homework assignments, but that's sort of the point. It's to kind of push you a little bit. But are you okay with just the base computations? Does anybody have any questions on that? Okay. All right. Layout requirements, everybody good on that too? Spacing, edge distance, hopefully that makes sense. And you understand why we have those layout requirements. Everybody good? Okay, let's talk about bolted connection design, because we haven't talked about that yet, and that's actually really easy, okay? If you have a connection that has 100 kips on it, and each bolt can withstand 10 kips, how many bolts do you use? Pretty simple, right? Just take the load, determine the shear capacity of a single bolt, and divide to get the number of bolts, okay? Now, I want for everybody to sort of pay attention to this part on step 2. You're determining the shear capacity of a single bolt. Whenever you're designing a bearing type connection, you just look up the shear capacity of a given bolt. If you're designing a slip critical connection, the only thing that changes is whether or not you're looking at a shear capacity or a slip capacity. And all you do is you look up both and take up the minimum. So it's really easy to adopt this procedure for slip critical connections as well. And then you just divide to get the total number of bolts, okay? And when you do this, you need to what I call select a pattern accordingly. And what I mean by that is you're very possibly going to do some math and find that you need 6.82 volts, you know. So you're going to need to round that up to 7 or 8, some sort of pattern that makes sense, you know. It's like you're breaking out your times tables from 3rd grade. You have to develop a pattern of volts that makes sense. Now you're going to lay out the connection according to prescribed requirements, and usually what that means is the minimum edge distance and either S-min or S-preferred. I will tell you on the homeworks and exams whether or not I want you to use the minimum or preferred. I'm not going to make you guess on that, so don't worry there. Probably step 5 is the most critical step, because just because you lay out a connection according to spacing requirements does not mean that it will meet the bolt bearing check. Now, on that last homework we just did, we had a phenomenal amount of bolt bearing capacity. It was huge compared to the bolt shear capacity, and that's fine for that connection. But then on the example that we did in class, bolt bearing was less than bolt shear. So just because the connection meets spacing limitations doesn't mean the bolt bearing limit state is going to be met. So you got to check it. Okay. It's possible that your connection fails according to bolt bearing. If so, you need to iterate. And I'm going to talk a little bit about what that means and what you should be doing. But does everybody kind of understand the process? Honestly, there's not really anything magical about this. I think you probably could have figured this out on your own, honestly. You know, get your factored load, shear capacity of a bolt, divide, get the number of bolts, lay it out, check bolt bearing. That's really all there is to it. Does anybody have any questions? All right, I want you to pay attention to this part. These are some additional items to consider, okay? The connection could fail in bolt bearing. It could. If it does, you have a few options, and I want you as structural engineers to know what those options are. The first is to increase the bolt spacing or the edge distance. And I would argue that this probably should be your first course of action. So for example, if you use 2-inch bolt spacing and the connection fails, maybe try 2.5-inch bolt spacing, because that's going to seriously increase your bolt bearing capacity, and it might be enough to push it over the finish line. So, and I'll go ahead and tell you on your first homework assignment, you might have to iterate. So make sure that you are that you've got these ideas in your back pocket. Okay. The other thing is to increase the number of bolts. I tend to not think that's a good idea unless you really need a lot more capacity. Like you selected 12 bolts and then you checked the bolt bearing capacity and it is phenomenally lower than the factored load, and you really need a lot more capacity. You could increase the number of bolts. I tend to not think that's a good idea unless you really need it. Now, another thing that you could do is if you have a bolted connection and it fails in bolt bearing, but it very, very slightly fails in bolt bearing, you could stagger the connection, because you're going to get a little bit of additional edge distance on some of those staggered bolts, and that could up your capacity, maybe just enough to get you across the finish line. I am not going to ask that you do that for any homework assignment in this class, but that's an option for you as a practicing engineer. Does that make sense? Okay. I also think you need to choose a bolt pattern that makes sense. So, and this is why iteration tends to not be a super big deal in a lot of connection layout problems. As an example, if you do the math and you need 10.46 bolts, are you going to round that up to 11? Or maybe just a grid of 12, like 3 by 4. You know, it kind of makes sense. But because of that, there's already a little bit of conservatism built into the connection. So you don't, in instances like that, you don't really need to iterate all that much. So it's something to keep in mind that you could make that a little easier on yourself. Okay. Some other items to consider. I am not going to have you do this on homeworks and exams, because I think it is valuable for you as students to understand the process, but I do want you to understand what happens a lot in real life. In real life, a lot of times fabricators will lay out connections according to 3-inch grids. So in their connection region, they'll draw a 3 by 3 grid, and that's where their bolts are. The reason why is 3-inch bolt spacing and 3-inch edge distance requirements meets all of the spacing and edge limitations for 3/4-inch bolts, 7/8-inch diameter bolts, and 1-inch diameter bolts, which is the most common bolt sizes that we use in typical steel construction. And it also, if you have a really, really big project and a lot of connections, 3-inch spacing is easy to convey. It's easy to understand. And so it can make the connections repetitive. Even if they are a little bigger than they need to be, making multiple repetitive connections using regular dimensions can speed up and economize the fabrication process. If you got to fabricate 100 of these things, it might be easier to just do them all the same, even if they are a little conservative. In some instances, instead of designing for an external load, we're not going to do this in here, but it's something else I wanted you to be aware of. Some instances, what we do is, and instead of designing for an external load, we design to develop what's called the full capacity of the tension member. So in step 1, we determine the factored load PU. And up until now, we've thought that the factored load is just 1.2 dead plus 1.6 live. Well, what we could do is we could treat the gross section yielding, net section fracture, what have you, capacity as the factored load. The idea is we know the member will fail under 200 kips in gross section yielding and 300 kips in net section fracture. And let's say those are the only 2 limit states we care about. So we'll actually design the bolted connection to withstand 200 kips. The idea is that the connection is stronger than the member. Does that make sense? So that is a means of designing a connection, is to not use an external load at all. And sometimes if you know you have a member that's going to see some heavy load, or if you're in the initial detailing process, it makes sense to just design for the capacity, or to design to develop the full capacity of the tension member. Does that make sense? Any questions? All right, I do want to get into this example, but considering that we're all here, I'd like to talk about slip critical connections, so I'm actually skipping ahead to the next lecture. I know that's a little bit atypical of me, but I'd rather take a look at slip critical connections if we're all here, given the possibility that we may be able to cancel class on Friday with our pending tour. So let's talk about slip critical connections, and I want to talk about this. So if you remember, I showed you this at the very first day that we first started talking about bolted connections. And if you remember, there is a difference between the blue forces, which are the applied external forces to a given system, and the orange forces. The orange forces are the resisting mechanisms that resist load. Now, what we get is we get 3 resisting mechanisms, 3 means of resisting load. We have the bolt coming into contact with the plate, that's bolt bearing. The shear developed in the shear plane between the 2 plates in the bolt, that's bolt shear. But then there's friction, right? If I have 2 plates and a bolt going through them, and I wrench the hell out of that bolt, what's happening to the plates? The plates are coming into contact, right? And if I take those 2 plates that are in contact and I yank on them, there at the connection, there is a friction developed between the 2 plates. I seem to remember something in statics or physics about taking the normal force multiplied by the coefficient of static friction, and that will tell me the friction between 2 planes in contact. Does that starting to sound familiar? Right? Well, we can count on that in typical steel construction. We can count on that friction. Okay? That friction is developed through a pretension connection. So what we're using is what's called a slip critical connection. So slip critical connections is where the slip or that friction developed between the 2 plates is something that we're counting on in a design scenario. Now, to install a slip critical bolt, the first thing that we have to do is we have to get the connection snug tight. Snug tight is considered either like a few hits of the impact wrench or the full effort of an iron worker. The idea is, again, snug tight is just the 2 plates in contact and the bolt is tight. That's what snug tight is. The snug tight's so if you want a shorthand definition, it's the condition in which the contact surfaces firmly bear on one another. But that won't give you the prescribed amount of tension that you need in a bolt. I mean, per bolt, we're talking about 20, 30 kips of tension, bearing in contact between these 2 plates. So we need to use a prescribed method necessary to achieve the required torque. Now, I'm curious how many of you have been on a DOH construction site where they've installed splices and bridges. I saw a few people raise their hands last time. Okay, I'm curious if you ever saw anybody doing this. You're shaking your head yes. A couple of people shaking your head, yes. Have you seen this before? This is the first and arguably the cheapest and most common way. I don't want to say cheapest, I'd say more traditional. The most common way of achieving a prescribed pretension, and this is called the turn of the nut method, right? So the idea is that you place match marks on the plate, the bolt, and then the nut, right? And so the idea is like this one right here. See how the nut is like a third of a turn away, right? So based on your bolt dimensions and based on what the spec says, the idea is you get it snug tight and you look it up. Okay, this is a third of a turn. So you place your match marks and you wrench that thing such that they match up, okay? And the idea is that by applying that additional amount of torque, you are achieving the required amount of tension or the required amount of normal force between the bolt or between the two plates. And just to be clear, all of these pretension methods tend to overpredict the or tend to overachieve the required amount of pretension. That's actually even reflected in the specification, and I'll show you that here in a little bit. But if you ever want any more details on this, you know how we've been turning to 16.1 whatever, 16.1-120, 16.1-130, right? Open your manual and go to the 16.2 pages. The 16.2 pages contain the RCSC spec, the Research Council on Structural Connections, and it contains much more comprehensive details for stuff like this. We're not going to refer to it very directly, but it's worth taking a look at because there's a whole nother set of specs in the back. There's actually a 16.2 and a 16.3 on like QA/QC stuff and whatnot. All right, that is one way to install a slip critical connection. The other is to use what's called a calibrated wrench. And so basically you just have a calibrated impact wrench that will deliver a certain amount of torque, but you have to calibrate that thing daily, okay? If you ever go onto the site, you'll see one of these things on the right clipped onto a member that they use to calibrate the wrench daily. Basically what you do is you stick a bolt through that hole and you use the wrench to tighten it until you hit the required tension. That thing on the right, a company called Skidmore Wilhelm tends to be a common manufacturer of those. And what they are is essentially a super duper hyper accurate bathroom scale. So the idea is you stick the bolt through the hole and it records the amount of normal force that you, or reports the required amount of normal force that you generate. But you got to calibrate it daily, okay? Now, one very common item that's getting a lot of use here recently by state DOTs and whatnot is the use of twist-off control bolts. This is something I mentioned earlier. This is one of the reasons why we have Group A, Group B, Group C classifications in the manual, because those bolts don't quite meet the ASTM spec, even though they have the same mechanical properties, right? And so this is another one of those very special wrenches, but the cool thing about it is that you only have to grip the wrench on one end, right? And what happens is the wrench will actually perform two turning actions. It turns both, or it grips the bolt and it turns the nut. And whenever you achieve the required amount of tension, that little splined end kind of chucks off. And so as an inspector, it's really easy to see which ones meet their pretension and which ones don't. So this is a little expensive, but it's quick, you know. And so in the land of external labor, driving prices and whatnot, it's got some money's worth. Yes, sir?
Do these ever get retorqued, or do they just have to replace the bolts to retort?
You're right. They pretty much have to do a replacement. But generally, so let me, was that my phone? It was my phone? I turned the little, I hit the little button to say leave me alone. No, I didn't. I'm sorry. There's the little switch that's supposed to say be quiet, and I didn't turn it. I'm sorry. Okay, so where was I? Oh, okay. So to answer your question, no, but here's the other thing. So if you're starting to get like corrosion problems at an area like that, you probably have much bigger problems. You're probably looking at total beam replacement and things like that. So, I mean, that is a downside, is that they're kind of tough to reinstall. What you can do is, if it's necessary, you can untighten them, replace them. If they get corroded, you maybe drill them out and whatnot. But I mean, pretty rare. So, I mean, the other thing that here, let me say it like this. So I think what matters most in exterior bridge applications is that you have proper drainage and proper corrosion protection systems and things like that. If you have that, it's usually not a problem. I mean, I can't speak to every pretension bolt installation. One maybe comes loose every so often, and if that's the case, it's easy to replace. But if we're talking about corrosion through a splice connection, there's probably a lot more you got to fix too. So it's a fair question. Any other questions? This is good stuff. Now, another method is what's called a direct tension indicator. I'm just trying to show you some of the stuff that you'll see in the field. A direct tension indicator is basically a super fancy washer, and the washer has these little like nubs on it, right? And so what happens is you are installing your bolt, and as you're tightening that, you're actually mashing these nubs. So this is before and this is after. And once you achieve a certain thickness between those two, the idea is that you achieve your required pretension. They have these little feeler gauges and whatnot that that they use to measure that. Nowadays, sometimes I know there's a product for DTIs that you don't need a feeler gauge, because what the washer looks like is if you turn it around, these things are hollow, and inside them is this like orange goop stuff. And it looks like a rubberized Play-Doh. And what happens is, as you are tightening the connection, once you hit that required torque, the orange goop kind of squirts out. So whenever you see the orange goop, you're good. So that's what it looks like. So
I'm sure that's cheaper than the twist off bolt.
Probably, yeah. But again, it goes back to how many of these things are you doing? If you're doing a ton of them, I mean, those twist-off control bolts, they're quick. I mean, they're expensive, but you're doing them so quickly that you start to ask yourself, is it worth it to pay the extra money per bolt if I can install them faster? And it just depends on labor prices and material prices that day. So, yep, time is money. Okay. With me so far? All right, so let me show you how to compute the capacity of a slip-critical bolt, but I want everybody to walk through, before you start breaking out your pencil and writing down equations, this is another one of those instances where you don't actually have to do the math, okay? Because remember with bolt shear, remember how we did the math and then we found, oh, there's a guide for that, right? Well, with bolt slip, there's a guide for that too. So the means of computing the capacity is through this expression here, okay? So first off, a couple things. The phi value is 1, okay? The phi value is 1 because we're considering deformation and whatnot at the service load. But keep in mind, when you look at your slip critical capacity, it is much less than what you get for bolt shear. One thing that I'll tell you is that if you're ever designing two connections for the same load, one being a bearing type, one being a slip critical, you will probably use double the amount of bolts for the slip critical connection, because you are relying on this effective friction to resist the load, but you aren't going to get as much friction per bolt as you are shear capacity per bolt. So you end up needing more of them, right? That make sense? And I talked last time about when you would use slip critical connections, bridges, seismic land, and whatnot. So you only use them if you need them, but if you need them, you're going to need extra bolts. So let's take a look at this. Okay, so in order to determine the capacity, you need the following. You need mu, you need this term, TB, and NS. Now the reason why I'm skipping over those other terms is because mu and TB, that's this. That's your coefficient of static friction and your normal force, okay? Right now, you can write this stuff down if you want, but you're going to see how this gets real simple real quick, okay? Now let's walk through what some of these other terms are, okay? So we have the resistance factor is 1. RN's obviously nominal slip resistance per bolt. Mu, that's our coefficient of static friction. In the manual, it's called a mean slip coefficient, but it's kind of the same thing. Du is just 1.13. Right? it feels kind of anticlimactic, right? That in steel design, there's always like a thing that goes into all these parameters. We have to compute the net area. We have to compute U. And then, oh, it's just 1.13. It seems kind of anticlimactic. What is that? DU is a multiplier. What it does is it reflects the amount of pretension that you get in the field versus what you specify. And the point is it's always higher, okay? You always get more pretension in the field than you actually specify. So much so that on average it's about 13% more. That comes from tests and whatnot of connections in the field. Now, you can use a higher value if you would like, as long as it's permitted and approved by the EOR. What's EOR stand for? Anybody know?
Engineers of Russia.
Apparently they're busy these days. The engineer of record.
Of what?
Of record.
Record?
Yeah.
Bookkeeper of the project?
EOR. Hi guys. I'll just stand in the corner. Yeah. Eeyore impression.
Yes, they meet specifications.
Oh my goodness, I'll have to. We have a lot of Winnie the Pooh toys for my daughter, so my wife is going to get a kick out of this. So, all right. So the thing about slip critical capacity is the computation is very easy because this is 1.13. H sub F is what's called a filler plate factor. For every problem that we do in this class, it's going to be 1. I'm going to explain what happens when it's not 1 and what it is. T sub B is the minimum fastener tension, and NS is just the number of slip planes. That's the same thing as the number of shear planes. So it's the same thing. So a lot of this is very easy. Now, the mean slip coefficients, we have 2 of them. The 2 slip coefficients are a function of our surface conditions. What is friction? It's contact between 2 surfaces. Depending upon the surface conditions, you're going to get a different coefficient of friction. Like steel on wood gives you different mu value than plastic on aluminum, right? It's a different interaction. Typically, the 2 values that we deal with are either 0.3 or 0.5. And 0.5 is used when we have like blast clean steel, like we're cleaning the steel because we want to get that extra friction. But more often than not, and unless otherwise stated, we're going to use a mu value of 0.3. The minimum bolt pretension, that comes in Chapter J. It's on 16.1-127. That is the one table I would turn to go through some of this math here in a bit. But this lists the minimum bolt pretension that we're trying to achieve in any of our bolts. So this is the amount of tension in that bolt. More often than not, it's about 70% of the nominal tensile strength of the bolt. That's about where these numbers come from. But we have Group A, Group B, bolt diameters, pretty easy. Now the filler plate factor, let me explain what that filler plate factor is. First off, it's always going to be 1 for us, but let me kind of explain what it is. So for you DOH folks, how many of you have ever seen these types of connections out in the field? Some of you are shaking your head. So this is a beam splice, right? So this is when we're taking beam A and splicing it with beam B. Now I want you to pay attention to the beams, especially this beam and this beam. It is very common in bridge applications and in building applications that when you're splicing a beam, you're splicing a beam where this beam and this beam have different flange thicknesses, right? So what happens is, okay, this flange, let's say it's a 1/2 inch thick, and this flange is a 3/4 inch thick, right? So when you stack your splice plates, what happens over here? There's a gap, right? And there's a gap of what, 1/4 inch? So we put in a 1/4 inch filler plate so that the 2 splice plates sit flat. Does that make sense? That's what a filler plate is. Whenever you have 1 filler plate or no filler plates, then HF is 1. It's whenever you have a bunch of filler plates that you have to use H sub F is 0.85. And the only time we would ever use multiple filler plates is when the dimensions are weird. When you have like a discrepancy of, I don't know, 5/16 maybe what you'll do is use a 1/4 inch and a 1/16 of an inch so you can get to that required thickness. Does that make sense? That's the only time you'd ever use multiple filler plates. More often than not, you're only going to use one. Make sense? All right, let me show you the math. This is really easy. Okay, what is the design slip resistance of a 3/4 inch diameter A325 bolt, assuming a Class A fang surface and only one slip plane? So no filler plates present. So mu is going to be 0.3 because that's Class A. Du 1.13. HF is 1.0 because we have no fillers. NS is 1. Single slip plane. Now what about the bolt pretension? How many of you turned it to table J3.1? Okay, so we have an A325, so is that group A or B? Group A. 3/4 inch diameter bolt, what's the bolt pretension? 28 kips. And then our phi value, oh my goodness. Starting subtitles. What? Is 1. So multiplying all these together, what's phi RN? That's all you got to do is just multiply them all together. $9.49. Do I have a second on that? Is there? I did this really quick, but does this make sense? All right. Let me stop for a second, see if anybody has any questions. Oh, that's table J3.1. No, and I'll tell you why. It is not tab worthy. What's that? Just wait. Just wait. Any questions? Well, that's true. It's pretty close there. But look, just watch. I want you to turn to table 7.1. No, this is the bolt table, bolt shear table. This is all the way. So you're used to this table on page 7-22. Then turn the page to page 7-24. This is, I would say this is tab worthy, but it's literally right next to the bolt shear table. Check this out. What did you say, 9.49? So what did we have? A 3/4 inch diameter bolt, Class A fang surface, Group A bolts, single slip, 9.49?
We only need to compute it then.
We just need to look it up. And why did I say that minimum bolt pretension was unnecessary? Look right here. It's right there.
What does the hole type mean?
Ah, that's a great question, the hole type. So these are standard holes. These are slotted holes loaded transversely. This is an oversized hole. This is a slotted hole loaded parallel to the slot. And this is a long slotted hole. So the idea is if you have a slotted hole, are you loading it this way or are you loading it this way? Because if you're loading it left to right, it's really not behaving any differently than just a standard hole. So this is a short slot loaded transversely, short slotted hole loaded parallel. That's a great question. There's specs in Chapter J that will tell you what that is per bolt diameter. What we've been doing by adding a 1/16 of an inch, that's a standard hole. Does that make sense?
So, I mean, once you get so big with the oversized, it's not going to work at all.
Wait, what? Well, I mean, yeah. There's a spec for that, is what I'm getting at. But what I'm interested that you can perceive is what do you think would happen to the slip capacity as that goes down? Look what's happening. See what's happening? The slip capacity is going down because the hole is getting bigger. We have less contact area to rely upon in terms of friction. Does that make sense? And to be honest, I mean, we use them every now and then. Like, as a bridge engineer, the most common non-standard hole that we use is slotted holes and expansion bearings and whatnot. But oversized holes and whatnot, they're not all that common in most building construction and bridge construction, except for like specialized instances. But for routine connections, not that common. There's a reason we call them standard holes, you know. It's a great question. Any questions? Everybody good? Would you like to do some real examples? All right, so this is the example we're going to look at. Now this is a bearing type connection, but we're going to take a look at what would happen if this was a slip connection. And you'll see how it would affect things. So we're going to design and lay out the bolted connection shown. We have a 12 by 7/8 inch plate lapped onto a 12 by 7/8 inch plate. So what does that mean for bolt bearing cases? I'm asking, what does it mean?
Single shear.
Well, it's in single shear, but the bolt bearing case, remember there was only 2 cases of bolt bearing? They're both the same is what I'm getting at. Like they're both 7/8 inch thick plate that are all the same steel. The spacing and edge distances are all going to be the same. So we're not going to have to worry about case 1 bolt bearing, case 2 bolt bearing. They're all the same. Does that make sense? All right. All right, I'll give everybody a sec to copy this down, and then we will get to it. All right. Everybody good? So what would step 1 be for this problem? Well, what would really be step 1?
Look up the GRN for 3x.
You're skipping ahead even further than that. Factored loads. So step 1, what is that? Got to break out your Casio FX 115 ES Plus or similar scientific calculator. Do you have a second on that? So we need a single bolt capacity. So help me out. We've got group BX. We have a bolt diameter, 3/4 of an inch, and we're in single shear. We're going to ignore slip for now. And so this is going to be that.
27.8.
What's that?
27.8.
27.8. Do I have a second on that? Okay, all right. So, how would we determine the required number of bolts?
Wasn't it the load over the factor?
There you go. So PU over phi RN, which is 394 kips. Why did I say 39.4? What is that?
14.2.
14.2? There you go. So we'll say try 15 bolts. Now, you want me to show you how this problem would change if it's a slip critical connection? Let's look at that. So everybody that's on table 7-1, turn the page. Let's assume a Class A fang surface. What's phi RN going to be for this problem? So we're in Class B bolts, or sorry, Group B bolts. So which table do we look at? Do we look at the page on the left or the page on the right? Look at the top of the table. What's the top of the table say? Group A bolts or Group B bolts? So if we had a Group B 3/4 inch diameter bolt and single slip, assuming a Class A fang surface, what do we get for phi RN? Say it again. 11.9 kips per bolt. And that's from table 7-3. What would that be in this case? Say it again. 33.11 bolts. What do you think we should use for a pattern? Maybe 35? You can do 5 times 7? Does that make sense? So that's the only thing that changes if this is a slip critical connection. Just that. That's the only thing that's different. You just have a different capacity, and instead of taking just this, you take the minimum of these two, but this is usually always smaller. Everything else is the same. Make sense? Now, We are using 15 bolts for this problem, so let's lay out this connection. We need an S and an LE. Now, the problem said, well, the problem didn't say what we're going to do. I know I said I would tell you that. So I'm going to tell you we're going to use S-min. Now, S-min is 8/3 of the bolt diameter, which is 8/3 of 3/4 of an inch, which is 2 inches. Now, how do we determine LE min? We look it up. My apologies, you have to keep turning the page. I can't do anything about that. 1 inch. Table J3.4. And so now the question comes, we have two ways of doing this. Do we do this? Or do we do this? Let me ask you this. If we did it this way and everything was even, what would this space be? How many do we have? 1, 2, 3, 4, 5, 6. Does that meet spacing limitations?
Oh, well, yeah,
It does, right? So, that being said, both of them would meet requirements, so which one would make sense, this one or this one? Well, that's just a bolt bearing check. That's just, I mean, so what I'm getting at is this. Whatever this is connected to has got to be longer on the left than it does on the right. Longer connection plate, more less money over here, right? So I propose, here's my connection. This is 2 inches. This is also 2 inches, 2 inches, 2 inches, and this dimension is 1 inch. Why am I saying it's a trial connection? What haven't I done? Well, but the other plate I can say is the same thing.
Make sure it works.
But what makes sure what works?
Bolt shear, bolt bearing.
Bolt shear and bolt bearing. Now, bolt shear we know works, right? Bolt shear we know works because bolt shear said that we needed 14.2 bolts and we have 15. We know that works. What have we not checked? The 1.2 LC-TFU, the 2.4 dB-TFU. We have to do the bolt bearing check, right? When we do bolt bearing check for this trial connection, how many edge bolts are we going to have? 5. And how many interior bolts? 10. So what do? We do the 1.4 LCE TFU, the 1.2 LC TFU, the 1.2 LCI TFU, the 2.4 dB TFU, right? Get an RNE, get an RNI, 5 RNEs, 10 RNIs gets us the RN, multiply it by phi, see if that's less than our load of 394. Or sorry, see if it's more than our load of 394. If it is, we know the connection's safe and that's our answer. If not, we may need to bump this up a little bit. What I might do is up this spacing by 1/2 inch and try it again. Here's what we're going to do. Given that it's 11:50, I am going to make a judgment call. I'm going to post a little video finishing this example. I'm going to cancel class on Friday. And I'm going to say that the homework that was due Friday and the homework that I was going to assign Friday, we're just going to make it all due Monday.
So we have 2 assignments on Monday?
Yes, but the second one's going to be quick. Is that fair?
So it can be slip connection.
Yeah, slip one. Yeah, if you can do this, you can do slip. So.
Are you going to post, because I know you had a problem for slip critical connection too, like a little example.
Yeah.
Put that in the video as well.
I will, because I'm a nice guy. See you Monday. I haven't decided if I'm going on the tour yet. If I can, I will. If not, I will see you on Monday.
So be here at 9:45 on Friday?
9:45 on Friday between the buildings. All right.